Now, at this point, you may well be thinking, well, that's a lot of theory. I mean, yeah, here's a prediction. Our models predict that the main sequence star will evolve into a red giant, and we find red giants. But that's not yet enough. We want to see, can I really show from observations that red giants evolve after main sequence stars, in other words, that one turns into the other. And we have a lab which will allow us to do this, and I suggested that this is going to be clusters, because remember, stars in a cluster, whatever their size, are going to all be formed at about the same time. Massive stars evolve faster. The later stages of evolution are rapid. So if I let a cluster evolve for some time and then stop, I should expect to find, say, lots of O and B stars, but no G stars. That would be a reasonable thing. If I find a bunch of G stars and O and B protostars, I've done something wrong. I need to imagine that the way that the cluster evolves fits what the model tells me. Flipping this around, once I trust my model, I can look at a cluster and figure out its age by figuring out which stars have evolved to what point. And moreover, it's in the context of clusters that spectroscopic parallax comes into its own. When we look at a cluster, all the stars are about the same distance from us. Whatever interstellar extinction and reddening is going on because of dust or clouds in between us and them is pretty much the same for all stars. So what we can do is, for these stars, brightness relative to each other corresponds to luminosity relative to each other, and color corresponds to color relative to each other. So rather than taking detailed spectrum of each star, what we have efficient ways of basically taking three filtered photometric results through three filters, doing what's called a color magnitude diagram, which basically plots the difference between two colors, two filters, and the sum of the filters, or one of them. That's basically brightness versus temperature. And there are errors in the temperature, and there's inaccuracies because of intergalactic reddening, but they tend to move, interstellar reddening, they tend to move the whole thing left and right. There are unknown extinction that moves, or distance, that moves everything up and down because we can't determine an absolute velocity. But by matching onto the main sequence, we can get, in large numbers of stars, a very accurate determination both of distance to the cluster and then of the absolute luminosities of all the stars there. So let's see a model simulation of how a cluster should evolve, and then we'll compare that to what we actually see. So Star Clock 2.0 is a very fun DOS-based simulation, and what it's going to do is it's going to create for us a collection of stars of various masses, and I'm going to run the simulation, and I can stop it, and we see that, let's see, about 800,000 years have passed. Stars with masses 9 solar masses and above have formed. The ones with the higher masses are in fact beginning to move off the main sequence. You see them moving off to the upper right. Lighter stars have not yet formed, so in 840,000 years you get down to 9 solar masses. Let the animation run some more. We're now down to 1.6 million years, and stars with a mass of 4 solar masses have formed, and the heavier ones are beginning to move off. At this point it pays to increase the time step because some things happen too slowly. But, let's take a few more slow steps just to see what's going on. The heaviest stars will start leaving the main sequence before the lightest stars show up. Here we go. We're starting to see horizontal branch behavior in the heavy stars. We said more massive stars and exit the main sequence earlier. And we're seeing that before the sun, were it in the sample, comes on into the picture, stars with masses of, say, 8 solar masses or more are already done with their main sequence lifetime and have disappeared. And notice the rapidity with which horizontal helium branch behavior is gone. This star is the 25 solar mass star is already done with helium burning and has probably generated a solar nebula. And we're down to 2.5 solar masses. And we again see very rapidly zipping through the final stages of evolution. Now that we get to the lighter stars, things slow down. So let me indeed up my time step. And now things will run 10 times as fast. And we finally are almost ready to have our sun come on the picture. And so you see, this is what the model predicts. These are the trajectories of stellar evolution that we should expect to see. And now, stop this. Anytime I hit a key and stop the simulation, this should be a possible configuration that we can find in actual clusters. So we go out and look around at clusters and make these color magnitude diagrams, and I will refer you to a beautiful database that will make them for you, and let's see how they jibe with reality. So that was a nice simulation. We now know what theory predicts. Now we go out to the lab, in other words, the universe, and do real clusters exhibit the properties that we saw in an order of increasing age. These are very, very young clusters. These kinds are called OB associations. They are clusters so young that hot O and B stars are still on the main sequence, so you don't expect to find many solar mass stars on the main sequence. Here is the color magnitude diagram. This is to be read very much like HR diagram. In other words, luminosity increases this way, temperature increases this way, and we see here it's very hard to figure out where the main sequence lies, but what is clear is that I guess probably somewhere around here would be the main sequence, and only the most massive of the stars have landed on it, and the less massive stars are a collection of protostars. The structure becomes more definite when you go to a young but relatively developed cluster. This is the Cone Nebula. That image that I prematurely erased is a beautiful Hubble image, which shows you, by the way, these dust cocoons that I spoke about in which new stars are forming. But if we look at the color magnitude diagram for this, we now see a well-defined beginning of a main sequence. And in fact, if you drew this carefully, you would see that the main sequence, let me correct myself, is probably something like this. And what we are seeing is that the more massive stars have joined the main sequence and less massive stars have not joined it yet. And the main sequence, the sort of the lightest stars already on the main sequence would tell you how old the cluster is. A slightly older cluster, again, this is familiar. This is a pretty image of the Orion Nebula. And here by now, by 12 million years of age, we see a very well-defined main sequence. And what we see, this is sort of a classic HR diagram, that would be the main sequence. We see that lighter stars are still on their way down. Remember, these are the evolutionary trajectories down to the main sequence. And the most massive stars are already on their trajectories away from the main sequence. So we have two sort of reference points here. We have what's called the turn-off point. That is the mass of those stars that are just beginning to leave the main sequence. And then we have, if you want, the turn-on point somewhere down here, which is the mass of those stars that are just becoming main sequence stars. And both of those, when you compare, have to give you equal ages. More to the point, one draws what are called isochrones, lines along which stars would lie at the same age, and matches to the cluster. And that's how we perfect our models, or the people who do that perfect their models. We can look at an older cluster, the Pleiades, well-established cluster, 130 million years old. And again, what we can see is that the main sequence turning point has moved to the right. Note, the main sequence turning point was well to the left of 0 over here, and it is a little bit to the right of 0 over here. Older clusters have redder, if you want, less massive turn-off points from the main sequence, and there are very few protostars left. In fact, we're beginning to see here the beginning of a population of white dwarfs from the more massive stars that have already lost their shells. Here's an even older cluster, 300 million years. Here, I've let the software helpfully designate for us a few red giants, and we very nicely see the main sequence turn-off points. Here's the Precipice, the Beehive. You can see that it's an old cluster just by looking at it. Look at all those reddish stars and very few that are blue. And indeed, the main sequence turning point is now, at about plus 0.3 in this color scale, so moving consistently to the right, though there are a few stars, those marked over here in blue, that don't belong. We also see a well-defined population of white dwarfs, but what these blue guys are, we do not understand. They are stars that are on the main sequence, even though they are past the turn-off point and should already have been gone. We'll return to those momentarily. Very old open clusters. Here's M67 and NGC 188. It's pretty easy to tell that the latter is older than the former. And finally, we come to globular clusters, the oldest clusters we find, but also the richest. So they produce very brilliantly rich color magnitude diagrams. Here's the color magnitude diagram for M13, and you see that with enough statistics, you can find both the main sequence and the turnoff point and the entire red giant branch and the horizontal branch, but no AGB stars. That goes too fast. Even in M13, we don't find any AGB stars. And again, you might ask, what's that guy doing over there? That's another one of those blue stragglers. They are particularly evident in this image. So globular clusters are the oldest star clusters. They're uniformly very old. And indeed, this is a picture of a very beautiful Hubble image of a pretty globular cluster, NGC 6397. And you look at it and you know there's something wrong. I understand where the yellow stars came from. What is all this blue stuff? Globular clusters are old. It turns out that this happens a lot, particularly in globular clusters. We have this phenomenon of blue stragglers. The mechanisms are still the matter of some debate, but probably a combination of two things. These stars did not start out as massive stars, else over the billion year or 3 or 5 or 8 billion year history of these stars did not start out as the high mass stars that we find them to be now, because over the 12 or 13 or whatever billion year history of this globular cluster, they would long since have evolved off the main sequence. They're still blue and on the main sequence, means they started out as less massive stars. They became so massive either by mass transfer in a close binary, a phenomenon we'll talk about later in the week, or by the collision and merger. Maybe they started off as 2 or 3 less massive stars that merged. We don't see many stellar collisions out where we live in the spiral arms, where stellar densities are very low. Our nearest neighbor is 4 light years away. But globular clusters are much denser, collisions are conceivable, and in fact it's likely that both mechanisms take place. And I spoke about the distinction between open clusters and globular clusters, and I said globular clusters are much, much older. Astronomers had traditionally made this distinction by distinguishing population 1 stars from population 2 stars, and initially it was a kinematic distinction. Population 1 stars were the ones that were moving around roughly the way the sun is around the Milky Way. Population 2 stars were moving in all kinds of other directions. Their proper motions and their Doppler shifts told us they had high peculiar motion. It turned out later that what was underlying this distinction, and what is now the definition of population 1 stars and population 2 stars, population 1 stars are metal rich. That does not mean that they're stars made of iron. The sun, with its trace contamination of carbon and oxygen and iron and calcium and so on and silicon, is a population 1 star that's called metal rich. The stars that we find in globular clusters are far more poor in metals, and so that we call the metal poor stars population 2. Now, since we know by now that the carbon and the calcium and the iron, as we'll see, that the sun incorporated into its nebula, that were there when the solar nebula formed, were actually formed by nucleosynthesis inside a previous generation of stars. What we conclude is that population 2 stars formed in regions where they were essentially the first or maybe the second generation of stars to form, whereas population 1 stars are forming in regions where there was much previous star formation. Notice that it's not a problem that the sun is 5 billion years old, because G-type star lives 10 billion years, but O and B-type stars that live, say, 5 million years can turn over many thousands of times in the time between, say, the formation of the Milky Way 13 billion years ago and the formation of the solar system 5 billion years ago. There was lots of time for lots of generations of stars to have lived and scattered their planetary nebulae around. And in fact, we conjecture, since there are some metals in the population 2 stars, the existence of a yet older generation called population 3. We've never seen them, I think, but we believe they were there. These would have been the first stars in the universe, or in any region in the universe, and they would have essentially been pure hydrogen and helium stars. And we'll talk later about how that changes their dynamics and why we think they must have existed.